Hello everyone, welcome to a new video to learn something new about Bayesian statistics. But in this part, I will start by frequency approach. So this is unit 9, unit 9, part 1, simple linear regression frequency approach. So simple means we have only one explanatory variable and one response variable. In this simple linear regression topic, we have three parameters we are interested in: beta 0, beta 1, sigma square. So at the beginning, we started by one population parameter, mean, and then population parameter. The first one is population proportion, and then population mean, and then two parameters, population mean and variance at the same time. But now we need to increase the number of parameters and need to know how to estimate by the Bayesian approach. But we follow the same approach, like likelihood, prior distribution, and then posterior distribution. So let's start by the frequency approach for the simple linear regression, in case that you haven't heard about the simple linear regression before. So simple linear regression frequency approach, and I will apply the idea on the house prices data set that is uploaded on Canvas. And in part 2, I will cover the Bayesian approach, and I will let you know what is next. In simple linear regression, we have two variables. We have two variables that can be measured on the same subjects. One is called the response, and the other one is called the explanatory variable. So why is response X explanatory variable? The researcher selected X because he thinks that the X can explain the variability in Y, because the values of Y are different. Why they are different? For many reasons. One of them is X values are different. So in the simple linear regression equation, the simple linear regression equation takes the form Y equal beta 0 plus beta 1 X I plus some error. So the two parameters we are interested in is beta 0, beta 1, and where is the third one? Is the variability of epsilon I is sigma square. So beta 0 means what? Beta 0 is the y-intercept, and it is the response on average when x equals 0. And beta 1 is the slope of the regression equation line, and it is the change in y on average when x change by 1 unit. This is the meaning of beta 0 and beta 1 in the simple linear regression. So what is the mean and variance of yi? Yi is some constant. This is the constant because we assume beta 0 is constant, beta 1 is constant, x's are constant, and the random variable is epsilon I. And we have some assumptions about epsilon I. Epsilon I follows normal distribution with mean 0 and sigma square, variance sigma square. Actually, we assume they are IID, independent, identically distributed normal with mean 0 and sigma square. So now those are the three parameters: beta 0, beta 1, sigma square. So what is the expected value of yi? Because we assume a distribution for yi. Whatever you are working with Bayesian approach or frequency approach, you assume some distribution for the data yi. So we need to know the mean of this distribution and the variance of this distribution. So the expected value of yi equals the expected value of beta 0 plus beta 1 xi plus epsilon I. So this one equals the expected value of beta 0 plus the expected value of beta 1 xi plus the expected value of epsilon I. Beta 0 is constant, so the expected value of a constant is the same value, plus beta 1 is constant, xi is constant, so beta 1 xi, plus the expected value of epsilon I is assumption, assumed 0, so I don't need to write down plus 0. So this one is the mean of I, or the mean of the value yi. The variance of yi is the variance of beta 0 plus beta 1 xi plus epsilon I. So this one equal the variance of beta 0 plus beta 1 xi plus variance of epsilon I. Beta 0 plus beta 1 xi is constant, so the variance of constant is 0 plus the variance of epsilon I, variance of epsilon I x is sigma square. So this is the expected value of yi, the variance of yi. So if I assume epsilon I is the difference between yi and beta 0 plus beta 1 xi, this one is called the residual, and the mean of this residual epsilon I by the assumption it is 0, and the variance of epsilon I by the assumption is sigma square. So the distribution of yi, the data distribution, the data distribution yi follows normal distribution with mean mu I plus, comma, the variance is sigma square. So this is the mean, and variance of yi. And it follows normal. Why it follows normal? This is data distribution, because actually y equal beta 0 plus beta 1 xi plus epsilon I. So yi is some constant plus the random variable. So random variable plus constant is a random variable, and the mean of yi is mu I, and the variance of yi is sigma square. So this is the data distribution. So to estimate the regression equation, we need the assumption of linearity. So this assumption is required for fitting the equation. If I would like to estimate only the regression equation, you assume linearity, because if the relationship is not linear, you should use some other formulas. The formulas I will show you in this lecture notes for the linearity relationship. But if the relationship between x and y, you can see this one from the scatter plot. If the relationship looks like it's not linear, you should work with the non-parametric regression. This one is not easy, but it's not in our course. This is a big course, another big course. So the linearity, the assumption is required for fitting. What if I would like to test beta 0 is 0 or not in the population, beta 1 is 0 or not in the population? I need more assumptions. The assumption about the errors. So the errors follows normal distribution. I need this assumption with mean 0 and standard deviation sigma. This assumption is required for inference. I mean confidence interval for the parameters, confidence interval for beta 0, confidence interval for beta 1, and confidence interval for sigma square, and also doing some tests for beta 0, beta 1, like the beta 0 is 0 or not, beta 1 is 0 or not. We need the three assumptions for the errors. They are independent, identically distributed normal with mean 0, sigma square. So you need to check the three assumptions if you would like to do testing or confidence interval for the parameters. But for fitting the equation or estimating the equation, you need only linearity. So in simple linear regression, we have three parameters need to be estimated and make inference about 1, 2, 3. So this case, I work with three parameters. So we need to know how to estimate these three parameters in the frequency approach, and also how to estimate these three parameters in Bayesian approach. Why you cover frequency approach? Because actually the frequency approach works with the likelihood that I need in Bayesian also. So we cover the likelihood because we need also this one in the Bayesian approach, because this is one of the three steps. In the three steps of the Bayesian is prior distributions, likelihood, posterior distribution. So what is the likelihood in this case? In simple linear regression, we have three parameters, beta 0, beta 1, sigma square. So let's drive the maximum likelihood of these three parameters. Let's write down the joint probability function first. The function of y, this is vector of y's, y1 up to yn. Given those ones are known, the joint probability function is the multiplication of all of them. So the normal distribution of y1 times the normal distribution of y2 times the normal distribution function of y3 times the normal distribution of the function y4 to the last one. So if I collected data and plug in the data in the equation, what are the data in this case? The y's and x's, yi values, xi values. Plug in these values in the equation, you get the likelihood. So in this one, you assume y is unknown and the parameters are known. This is the density function. But if you assume y is known and the parameters are known, this one is called the likelihood. So you plug in y's and x's in the equation. Now the equation or the function is a function of sigma square, beta 0, beta 1. So this one is called the likelihood. So how did you come up with this likelihood? Again, you assume yi given those parameters and xi follows normal distribution with mean mu I and sigma square, and they are independent. This is random sample. So because they are independent, the joint probability function is the multiplication of all these ones. This is the normal distribution for y1, and this is the normal distribution y2 up to the normal distribution of yn. The multiplication of all of them, because they are independent, so this is the multiplication, and this is the joint probability function. If beta 0, beta 1 sigma square is known and yi's are unknown. But now if I collected data, plug in the data in y and x's, now and the parameters are unknown, this is the likelihood. So this is how we came up with the likelihood. How do I find the maximum likelihood estimators for these three parameters? The same approach we have followed before. Write down the likelihood. Take the log of the likelihood. This is the log likelihood. Now, if you took the derivative of this likelihood with respect to beta 0 and then set equal 0 and solve the equation, you will find this is the equation. If you took the derivative with respect to beta 1 and set equal 0, solve the equation in terms of for beta 1, you get this is the formula for the maximum likelihood estimation for beta 1. If you took the derivative with respect to sigma square and then set equal 0, you will find sigma hat square is this one. So those are the three maximum likelihood estimators for the three parameters. This is the frequency approach. And actually these three formulas, also they are the least square regression method, coefficient parameter estimators as well. So the two methods in the frequency approach gave me the same formulas. The least square regression method and the maximum likelihood method gave me this one. So now let's practice on some real data set. I uploaded a real data set called house prices on Canvas, and this data set has six variables: taxes, number of bedrooms, number of passes, house price, house size, house lot size. And this data set is used to predict the price house. So let's select one of the explanatory variables. Let's select the house size because it is very associated with the price. So let's work with this one as X and this one as Y, because this is the one I would like to predict, the house price given house size. So the house price is Y and the explanatory variable is the house size X. So let's fit the regression equation. So should I do by hand? Let's use R. So let's use R to fit the regression equation and let you know what are the function in R should I use. So you upload the data first into R, and this is the path on my computer, but it may be different on your computer. For sure, it will be different on your computer. So, and then use the price, is the price in the data divided by 1000 y and divide by 1000, because I know I would like the numbers to be small because the numbers are very big. So I need to change the house price by thousands. And then I select the size as explanatory variable, and then I grab the size versus price because I need to make sure the association is linear. Looks like linear, positive association between X and Y. So now I can fit the equation because linearity is satisfied. So now I can use the LM function, linear model function, and I give the response tilde the explanatory variable. And I save the results under model, name model, and then I ask for the summary for the model. Now let's see how do I read the output of R. For the residuals, like the epsilon I, I equal 1 up to n, the minimum is this one, the maximum is this residual. The first quartile, third quartile, the median of the results. And then give me the ones I'm interested in. This one is beta 0. This one is beta 1. The estimates for beta 0, beta 1. And this is the standard error of the estimate beta 0 and this is the standard error of estimate beta 1 This is the t-value, the test statistic value that is used to test beta 0 equals 0 against beta 1 beta 0 doesn't equal 0. So this is H0. Beta 0 equals 0, beta 0 doesn't equal 0. So beta 0 in the population, because I work with a sample, this value comes from a sample. But we are asking about beta 0 and the population is 0 or not. So how do I calculate this t-value? This t-value is calculated as beta 0 minus 0 divided by square standard error of beta 0 And this t-value is beta 1 minus 0 divided by the standard error of beta 0 So I use these t-values. To find the p-values to see I reject or fail to reject H0. The p-value for beta 0, p-value is 0.397. This one is greater than 0.5. So we fail to reject H0. It means beta 0 in the population actually is 0. I should fit the equation without intercept. Can I fit the equation without intercept? You can do it. So it means the straight line should go through the origin point. It shouldn't hit the y-axis at some point different from 0. This is the meaning. The second p-value is used to test H0. Beta 1 equals 0 versus H1. Beta 0 doesn't equal 0. Beta 1 doesn't equal 0. It means the slope is 0 or not in the population. So if we fail to reject it 0, it means beta 1 equals 0. It means the slope equals 0. It means there is no association between x and y. But if we rejected H0, it means there is an association between x and y. So you use the second p-value. P-value is very small, very, very small, less than 5%. So we reject H0. It means beta 1 is not 0. It means there is an association between house price and house size at 5% significance level. So this is the meaning of these two p-values and the goal of these p-values. I use them to test these two assumptions, two hypotheses. Sorry. So what about the other output? Let's talk about the other output. This one is the residual standard error. This is the estimation of sigma square. Estimation of sigma hat. And what is this value? The adjusted R square or the R square? This adjusted R square 7552, it means 57.52% of the variability in house price can be explained by the house size. So this is the meaning of the R square adjusted in general. This is the proportion of the variability in the variability in the response that can be explained by the explanatory variable. So because you know the house prices are different. Why they are different? Because of many reasons. One of them is the house sizes. The sizes of the houses are different. So because the house sizes are different, the prices are different. So how much is the variability and the house size can explain the variability in the price house? 57.5, 52%. 100 minus 57.52, this is the proportion of variability or the percent in variability in the house price that can be explained by all the other variables, like the age of the building, the location of the building, and so on. So what about this p-value? This p-value is used to test the whole model is significant or not. So this one is used to test H0. Beta 0 equal beta 1 equal 0. All of them are zeros. Again, it actually should be beta 1 only. But we have only one parameter, beta 1. Because if we have multilinear regression, we may have 3 explanatory variables. So the null hypothesis will be beta 1 equal beta 2 equal beta 3 equal 0, versus at least one is different from 0. But because this is one is simple linear regression, we have only one beta 1. We have only one explanatory variable. So the conclusion from this one will be the same conclusion from this one. So beta 1 equals 0 versus beta 1 doesn't equal 0 again. But in general, it will be something like H0 if we have multilinear regression. Beta 1 equal beta 2 equal up to beta p. All of them are zeros. Against H1, at least one is different from 0. At least one of the variables has some impact on the response. But H0, it means none of the explanatory variables have some impact. But because it is simple linear regression, they are equivalent. The testing only this one or testing the whole model. So p-value is small, less than 5%. So we reject H0. It means at least one of the explanatory variables has some impact on the response, but it's actually only one. But in the multilinear regression will be different. So the house price data, check the assumptions. We need to check the assumption actually before this conclusion. In this one, I said beta 0 is 0 in the population and beta 1 is not 0 in the population. But actually, I shouldn't look at this one before I check the assumptions, because there are some assumptions for this inference. The assumptions are normality, equal variance, independent. So let's check the normality first. I grabbed the QQ blood, these ones, and then I grabbed the QQ line, this one. If the dots are very close to the straight line, it means normality is satisfied. But this is subjective, because what about those guys are not very close to the straight line? So I should do a test. So let's do a test like Shapiro test. But there are many other tests if you are interested. The Shapiro test, H0 mean the assumption is satisfied. Normality is satisfied. H1, normality is not satisfied. It is always like this one. And then look at the p-value. The p-value is big. P-value is greater than 5%. So the assumption is satisfied. Normality is satisfied at 5% significance level. So normality is satisfied at 5% significance level. So let's look at the other assumptions. The second assumption is independence. Independence. So we use this graph and the Durbin-Watson test, but there are many other tests. So the graph, you graph the order of the residual versus the value of the residual. And you graph the zero line. If you see any kind of form, it means it means the independence is not satisfied. I do not see any form. I see the dots are randomly scattered above and below the zero line. But if you have something like this one, I see some kind of form. So it means independence is not satisfied. It means I can fill this line and predict this value given the previous value. So every value depends on the previous ones. Or you can see something like this one. This one also means there is some dependency. But if I see the dots are randomly scattered above and below the straight line, and I do not see any kind of form, it means independence is satisfied. But if you would like to do a test, it's fine. Let's do the Durbin-Watson test. H0 for Durbin-Watson test is always independence is satisfied. The assumption is satisfied. H1, independence is not satisfied. Then I look at the p-value. The p-value is 0.832. It's very big. So it is greater than 5%. So we fail to reject H0. It means independence satisfied. So the second assumption is satisfied. Let's look at the third one. Constant variance. By graph, you look at the fitted values versus residuals. And then you graph the zero line. If you see any kind of form, it means there is no equal variance is not satisfied. Let me give you a very common one, which is equal variance is not satisfied. If you see the variability is small and gets bigger, variability is higher, variability is higher, variability is higher. This one is very common when the unequal variance is not satisfied. You see the variability increases when the fitted value increases. In this case, equal variance is not satisfied. But when I look at this one, I see it is not, I do not see this kind of pattern. So constant variance is satisfied. Constant variance satisfied. So the three assumptions are satisfied. So now I can conclude this one. Beta 0 is 0 in the population, but beta 1 is not. So it means there is some association between the price house and the house size. This is how to read the R output and test the three assumptions for inference, confidence interval, and test of hypothesis. So now if I would like to use the equation to predict, it's very simple. We need to write down the equation in general. Y equals Y hat, the predicted value equal 9.16 plus 0.077x. So I can predict the value of y at some given value of x. So I need to know what is the predicted value at x equal 1150. So just plug in x equal 1150 in the equation, you get y hat equal 9.16 plus 0.077 times 1150. You give 97.71 thousands of dollars. This is how to use the equation to predict. But this is frequency approach. But now, if I would like to cover Bayesian approach, I will use the likelihood again, but I will multiply the likelihood but by the prior distributions, and you get something proportional to the posterior. And if you are able to find the marginal posterior distribution of each parameter, you can use these marginal posterior distributions to make inference and estimation. But if you are not able, find the conditional posterior distribution, which is very easy to find them, and use the conditional posterior distribution for beta 0, for beta 1, for sigma square. Use the 3 conditional posterior distribution to randomly select a sample from the marginal posterior distribution of the 3 parameters. This is the simple linear regression in Bayesian approach. Thank you so much, and see you on the next video for the Bayesian approach. Thank you.